In mathematics, a dihedral group is the group of symmetries of a regular polygon, which includes rotations and reflections. Dihedral groups are among the simplest examples of finite groups, and they play an important role in group theory, geometry, and chemistry. Notation. There are two competing notations for the dihedral group associated to a polygon with n sides. In geometry the group is denoted Dn, while in algebra the same group is denoted by D2n to indicate the number of elements. Coxeter notation is another notation, denoting the reflectional dihedral symmetry as n, order 2n, and rotational dihedral symmetry as n plus order n. Orbifold notation gives the reflective symmetry as *n and rotational symmetry as n. In this article, Dn refers to the symmetries of a regular polygon with n sides. Definition. Elements. A regular polygon with n sides has 2n different symmetries, n rotational symmetries and n reflection symmetries. The associated rotations and reflections make up the dihedral group Dn. If n is odd, each axis of symmetry connects the midpoint of one side to the opposite vertex. If n is even, there are n, two axes of symmetry connecting the midpoints of opposite sides and n, two axes of symmetry connecting opposite vertices. In either case, there are n axes of symmetry and 2n elements in the symmetry group. Reflecting in one axis of symmetry followed by reflecting in another axis of symmetry produces a rotation through twice the angle between the axes. The following picture shows the effect of the 16 elements of D8 on a stop sign. The first row shows the effect of the 8 rotations, and the second row shows the effect of the 8 reflections. In each case acting on the stop sign with the orientation as shown at the top left. Group structure. As with any geometric object, the composition of two symmetries of a regular polygon is again a symmetry of this object, with composition of symmetries to produce another as the binary operation. This gives the symmetries of a polygon the algebraic structure of a finite group. The following Cayley table shows the effect of composition in the group D3. R0 denotes the identity, R1 and R2 denote counterclockwise rotations by 120 degrees and 240 degrees respectively, and S0, S1 and S2 denote reflections across the three lines shown in the picture to the right. For example, S2 S1 equals R1, because the reflection S1 followed by the reflection S2 results in a rotation of 120 degrees. The order of elements denoting the composition is right to left, reflecting the convention that the element acts on the expression to its right. The composition operation is not commutative. In general, the group Dn has elements R0, Rn1 and S0, Sn-1, with composition given by the following formulae. In all cases, addition and subtraction of subscripts are to be performed using modular arithmetic with modulus n. This lets us represent elements of Dn as matrices, with composition being matrix multiplication. This is an example of a group representation. For example, the elements of the group D4 can be represented by the following 8 matrices. In general, the matrices for elements of Dn have the following form. Rk is a rotation matrix, expressing a counterclockwise rotation through an angle of 2 pi k n. Sk is a reflection across a line that makes an angle of pi k n with the x-axis. Small dihedral groups. For n equals 1, we have DIH1. This notation is rarely used except in the framework of the series, because it is isomorphic with Z2. For n equals 2, we have DIH2, the Klein 4 group. Both are exceptional within the series. DIH1 and DIH2 are abelian for each other value of n. Dyn is not abelian. Dyn is a subgroup of the symmetric group Sn for n3, since 2n greater than n. For n equals 1 or n equals 2, for these values, Dyn is too large to be a subgroup. The inner automorphism group of DIH2 is trivial, whereas for other even values of n, this is Dyn Z2. The cycle graphs of dihedral groups consist of an n-element cycle and n two-element cycles. The dark vertex in the cycle graphs below of various dihedral groups represents the identity element, and the other vertices are the other elements of the group. A cycle consists of successive powers of either of the elements connected to the identity element. The dihedral group is symmetry group in 2D and rotation group in 3D. An example of abstract group Dyn, and a common way to visualize it, is the group Dn of Euclidean plane isometries which keep the origin fixed. These groups form one of the two series of discrete point groups in 2 dimensions. Dn consists of n rotations of multiples of 360 degrees, n about the origin, and reflections across n lines through the origin, making angles of multiples of 180 degrees, n with each other. This is the symmetry group of a regular polygon with n sides. Dihedral group Dn is generated by a rotation r of order n and a reflection s of order 2 such that in geometric terms, in the mirror a rotation looks like an inverse rotation. In terms of complex numbers, multiplication by and complex conjugation. In matrix form, by setting and defining and for we can write the product rules for Dn as the dihedral group D2 is generated by the rotation r of 180 degrees, and the reflection s across the x-axis. The elements of D2 can then be represented as E, R, S, Rs, where E is the identity or null transformation and Rs is the reflection across the y-axis. D2 is isomorphic to the Klein-4 group. For n greater than 2, the operations of rotation and reflection in general do not commute and Dn is not abelian. For example, in D4, a rotation of 90 degrees followed by a reflection yields a different result from a reflection followed by a rotation of 90 degrees. Thus, beyond their obvious application to problems of symmetry in the plane, these groups are among the simplest examples of non-abelian groups, and as such arise frequently as easy counterexamples to theorems which are restricted to abelian groups. The two n elements of Dn can be written as E, R, R2, Rn-1, S, Rs, R2s, Rn-1s. The first n listed elements are rotations and the remaining n elements are axis reflections. The product of two rotations or two reflections is a rotation. The product of a rotation and a reflection is a reflection. So far, we have considered Dn to be a subgroup of O, i.e., the group of rotations and reflections of the plane. However, notation Dn is also used for a subgroup of SO which is also of abstract group type Dyn, the proper symmetry group of a regular polygon embedded in three-dimensional space. Such a figure may be considered as a degenerate regular solid with its face counted twice. Therefore it is also called a dihedron, which explains the name dihedral group. Examples of 2D dihedral symmetry: 2D D6 symmetry, the red star of David; 2D D24 symmetry, Ashoka chakra, as depicted on the national flag of the Republic of India. Equivalent definitions. Further equivalent definitions of Dyn are: the automorphism group of the graph consisting only of a cycle with n vertices. The group with presentation, or from the second presentation follows that Dyn belongs to the class of Coxeter groups. The semi-direct product of cyclic groups zinc and Z2, with Z2 acting on zinc by inversion, is isomorphic to Dyn if is the identity and is inversion. Properties. The properties of the dihedral groups Dyn with n3 depend on whether n is even or odd. For example, the center of Dyn consists only of the identity if n is odd, but if n is even the center has two elements, namely the identity and the element Rn2. This is inversion, since it is scalar multiplication by -1. It is clear that it commutes with any linear transformation. For odd n, the abstract group DIH2n is isomorphic with the direct product of Dyn and Z2. In the case of 2D isometries, this corresponds to adding inversion, giving rotations and mirrors in between the existing ones. If M divides N, then Dihn has n m subgroups of type Dihm, and one subgroup Zm. Therefore the total number of subgroups of Dihn is equal to D plus sigma, where D is the number of positive divisors of N and sigma is the sum of the positive divisors of N. See list of small groups for the cases N8. The dihedral group of order 8 is the smallest example of a group that is not a T-group. Any of its two Klein 4-group subgroups has as normal subgroup order 2 subgroups generated by a reflection in D4. But these subgroups are not normal in D4. Conjugacy classes of reflections. All the reflections are conjugate to each other in case n is odd, but they fall into two conjugacy classes if n is even. If we think of the isometries of a regular n-gon, for odd n there are rotations in the group between every pair of mirrors, while for even n only half of the mirrors can be reached from one by these rotations. Geometrically, in an odd polygon every axis of symmetry passes through a vertex and a side, while in an even polygon there are two sets of axes, each corresponding to a conjugacy class, those that pass through two vertices and those that pass through two sides. Algebraically, this is an instance of the conjugate Solow theorem. For n odd, each reflection, together with the identity, form a subgroup of order 2, which is a Solow 2 subgroup, while for n even, these order 2 subgroups are not Solow subgroups because 4 divides the order of the group. For n even, there is instead an outer automorphism interchanging the two types of reflections. Automorphism group. The automorphism group of Dihn is isomorphic to the holomorph of Z, and Z, i.e., to Hol, and has order, whereas Euler's totient function, the number of k in coprime to n. It can be understood in terms of the generators of a reflection in an elementary rotation, which automorphisms are inner and outer depends on the parity of n. For n odd, the dihedral group is centerless, so any element defines a non-trivial inner automorphism. For n even, the rotation by 180 degrees is the non-trivial element of the center. Thus for n odd, the inner automorphism group has order 2n, and for n even the inner automorphism group has order n. For n odd, all reflections are conjugate. For n even, they fall into two classes, related by an outer automorphism, which can be represented by rotation by. The rotations are a normal subgroup. Conjugation by a reflection changes the sign of the rotation, but otherwise leaves them unchanged. Thus automorphisms that multiply angles by k are outer unless. Examples of automorphism groups. Dih9 has 18 inner automorphisms. As to Di symmetry group D9, the group has mirrors at 20 degrees intervals. The 18 inner automorphisms provide rotation of the mirrors by multiples of 20 degrees, and reflections. As isometry group, these are all automorphisms. As abstract group there are in addition to these, 36 outer automorphisms, e.g., multiplying angles of rotation by 2. Dih10 has 10 inner automorphisms. As to Di symmetry group D10, the group has mirrors at 18 degrees intervals. The 10 inner automorphisms provide rotation of the mirrors by multiples of 36 degrees, and reflections. As isometry group there are 10 more automorphisms. They are conjugates by isometries outside the group, rotating the mirrors 18 degrees with respect to the inner automorphisms. As abstract group there are in addition to these 10 inner and 10 outer automorphisms, 20 more outer automorphisms, e.g., multiplying rotations by 3. Compare the values 6 and 4 for Euler's totient function, the multiplicative group of integers modulo n for n equals 9 and 10, respectively. This triples and doubles the number of automorphisms compared with the two automorphisms as isometries. The only values of n for which phi equals 2 are 3, 4, and 6, and consequently, there are only 3 dihedral groups that are isomorphic to their own automorphism groups, namely Dih3, Dih4, and Dih6. Inner automorphism group. The inner automorphism group of Dyn is isomorphic to Dyn if n is odd, trivial if n equals 2, Dyn, Z2 if n is even and n greater than 2. Generalizations. There are several important generalizations of the dihedral groups. The infinite dihedral group is an infinite group with algebraic structure or similar to the finite dihedral groups. It can be viewed as the group of symmetries of the integers. The orthogonal group O, i.e., the symmetry group of the circle, also has similar properties to the dihedral groups. The family of generalized dihedral groups includes both of the examples above, as well as many other groups. The quasi-dihedral groups are a family of finite groups with similar properties to the dihedral groups.